Okay, let's do this the hard way. Hey everybody. Sorry for the delay. I was trying something new. I was trying to pipe the video directly from my phone. I tried it this morning and it worked, but for some reason, again, nothing works in this room. It drives me crazy. So once again, we have no video because this room is cursed. It's bizarre. But I'm recording the audio and you could link it again to the slides later on. I tried. So this is the last class, even though we have a class scheduled on Friday, because I'm canceling Friday's class. Why? Because every year I leave one lecture free for the TA to be able to present some of his work. And this year we didn't get that organized in time. It doesn't make any sense for him to give a guest lecture in the last class, so screw him. Didn't get to do it this year. So instead, on Friday, don't come here. But if you have any questions, you can come to my office. I'll have special office hours in my office, THN 208, when class is going on. So that's available to you. As well, this evening, or this afternoon at 2:30, the Mentor Center has a special session just for this class, organized by a former student of mine, Laura, and that is in E015 at 2:30. Okay, so if you have any particular burning issues with content in this class, you can go see Laura at 2:30 at E015 in the site building. Right? Any questions about Friday or Laura or site building or stuff? Yeah? Good. So today is just review, and we'll touch upon stuff you need for the final exam. Yeah, final exam. And as you know, your data analysis assignment is due this evening. A bunch of you have already submitted it, so things are progressing nicely. So, what have we done since the midterm? Oh yes, the exam is not cumulative, right? It's only everything since the midterm. And this is what we've done since the midterm. What? What's going on? All right. This is a good thing, right? All right. I don't want you to forget all that stuff before the midterm, though, because that's important stuff that you need for the rest of your career. It's just for the purposes of this class and testing and stuff like that, you can put that aside. So since the midterm, we have done the one-way ANOVA. We've also looked at what a two-way and an n-way mean, but we know how to do the one-way. We know how to do chi-square and McNemar's test, or McNemar's test is for the paired circumstance. We looked at ranked correlation, so how to do a Spearman's row manually. We looked at linear regression, how to do that manually. We also looked at, what it takes to do a multiple regression, even though we're not doing that manually. And we did on the YouTube class last week, which I'll go over again today because I understand the audio wasn't that great. Basic sample size calculation. I mean, really basic. So this is the stuff computationally that we covered. Theoretically, there's more, but this is the stuff that you should be able to do with your hands and a piece of paper and a calculator. Right. So we also learned about, but did not do, variations of the chi-square. Like what? What's a variation of the chi-square? Fishers. This means Fishers. Fishers test and Mann-Whitney-U test and the other one, Wilcoxon's rank test. Okay. We looked at two-way and n-way, as I mentioned. And we looked at multiple regression, as I mentioned. So let's go over some of these. The ANOVA. That's ANOVA, by the way. Get it? Yeah? All right. So it tests whether the means of different groups are different. It's the equivalent to a t-test, but with several groups. Okay? And the purpose is to find out whether or not the groups that you've chosen are in fact chosen from a theoretical superpopulation that has a specific mean. And if it is, then statistically, those groups you have chosen should theoretically have that same mean. And there are three types again, the one-way, the two-way, and the n-way. And that is defined by the number of variables, the number of dependent variables. So in this class, we only did the one-way again, but I want you to know when we would use the two-way and the n-way. For example, if we are comparing the mean bacterial count in 4 samples of milk, which version of the ANOVA are we applying there? One way. Why is that? How many variables are there here? There's one categorical variable, exactly, and one continuous variable. So the continuous variable is the bacterial count, and the categorical is the samples of milk. Okay, so it's the number of categorical variables that determines which one it is. So the second one is going to be comparing the mean weight of men versus women among Canadians versus Americans. So which are the categorical variables? There are two of them, gender and nationality. So that's a two-way. And lastly, the mean price of 6 categories of vegetables in 4 different grocery stores in 7 different countries. So price is a continuous variable, but how many categorical ones are there? Vegetables, that's 1. Grocery stores, that's 2. Countries, that's 3. So that would be a 3-way or an n-way. Okay, so that stuff should be burnt into your frontal lobes by now. So, as mentioned, the dependent variable is the continuous one, the one that we're doing the means of, and the independent one is the category, the nominal level thing. Sources of variation. The thing about ANOVA is we care about the between group variance and the within group variance. So between the different, well, you know what I'm talking about, right? So we have to compute both of those. And we compute both of those, we divide them, and we get the F ratio. That's the between group variance divided by the within group variance. This is some of the theoretical stuff that'll come out that I want you to be able to recognize. So we compute the F statistic and the degrees of freedom. So the degrees of freedom between groups is the number of nominal categories minus 1. So the number of categorical variables minus 1, and the number of the degrees of freedom within groups is this number minus the total number of groups. All right, this stuff you did already for your analysis assignment, so you know this stuff already. Okay, so we did the sums of squares in ANOVA, right? And when we take the sums of squares between groups divided by the degrees of freedom, take a ratio, that's our F. So that's the stuff I want you to be able to do in an example on the exam, much like the analysis assignment. Okay, so what's the null hypothesis for an ANOVA? Thank you, the means are equal. Just shout it out. It's the last class, doesn't matter, doesn't matter. So the means are equal, or you can write it that way statistically, and the alternative is that they're not equal. In other words, not the null. Okay, chi-square is that ridiculous formula there, and it tests whether two categorical variables are related. Do they have a relationship? Not whether one causes the other, but whether they're related, whether the degree of variation is not attributable by chance alone. And we have these other ones that we care about. We care about the Mann-Whitney-U test and the Kruskal-Wallis test. So Mann-Whitney-U is for ordinal measures, and Kruskal-Wallis is when there's 3 or more groups and ordinal measures. So again, we don't do these, but I want you to know this chart so that you know when to apply them. So the null hypothesis for the chi-square is that they are independent, so they're not related to each other, or the proportions are equal. The alternative hypothesis is that they are not independent, i.e. they are dependent. Got the logic straight there? So to do this, we create a contingency table. Most commonly, we have the 2 by 2 table, but it's possible to have 3 by 2 or 8 by 12 or any number of possibilities. And like always, we have to compute a degrees of freedom. And the assumptions are obviously the things that I'm going to quiz you on when it comes to the theory, because people always kind of screw up the assumptions. I mentioned that PhD student that I examined who had the assumptions wrong on her final PhD defense. That's problematic. So we have random sampling from the population. We have the observations are independent. We have the expected and observed frequencies. So the observed frequencies, the cell counts can't be less than 5, and the expected ones can't be 0. Right? So again, the textbook might say 10 here, but I'm going with 5. 5 is the rule that we use in real life. 5 is the rule on the exam. That's our formula. And our degrees of freedom, number of rows minus 1 times number of columns minus 1. And the steps are, we state the null, always state the null. We create the table. We check your assumptions. If the assumptions don't work, we can't do the test. We compute the expected frequencies, compute the chi-squared, and look up in the back of the book right? So if the back of the book is bigger than our number, then we fail to reject. We always want our number to be bigger. Then we did ranked correlation. What is this? What's that? That's, a picture of causation. Apparently, there's a correlation between ice cream sales and bank robberies, or guys carrying big sacks. Interesting. And apparently they're both caused by the friendly sun. Oh, so it's fake correlation. So we test whether or not two ordinal variables are related for rank correlation. Before the midterm, we did Pearson's correlation, which is for continuous variables. For this, we're doing ranked correlation. I may ask a couple of questions about Pearson's as well if they're relevant, because that's part of the stuff that came after the midterm. So it's a form of Pearson's, Spearman's is, but the variables are ordinal. Okay, so remember that Pearson's tested for a linear relationship, a straight line, and Spearman's test for a monotonic relationship. Can you draw me a picture of a monotonic relationship? With your hands? Yeah, there it is. I actually can't see that the wrong way, so I'm assuming it's right, because you're doing this. But the fact that you did that alone tells me you got it right. Okay, so ranked or unranked? People's preferences in ice cream flavors with calorie count. Is that a ranked situation or an unranked situation? Shout it out. That. Right. Thank you. It's ranked because preferences automatically is a ranking situation. It's on the slide anyway, so the answer is in front of you. Okay, children's age and height. Both of those are continuous variables, therefore unranked. Thank you. Property tax with number of rooms. That's a tough one because number of rooms could be either ranked or unranked. We tend to think of it as ranked, however. And this one here is our favorite world cities and their average temperatures. So temperature is continuous. Again, that word favorite or preference, that's a giveaway. That's ranking. So there it is. Straightforward. So our formula for, did I knock my thing off? I did, didn't I? So my formula for rank correlation is that. The distance, D is the difference in ranking, and our degrees of freedom is given by that. Right? And we remember how to do the details. So as well, we moved on and we did linear regression. Linear regression is finding the best straight line that describes the grouping of two continuous variables. And remember, our linear regression looks at the ordinary least squares effect, which makes the smallest distance between these points and this line vertically. Not orthogonally, but vertically. Okay, I said that. So we have a bunch of values for x. We try to figure out the best values for a y-intercept and a slope such that the distance between x and that line are minimized. Okay, we cover that lots of times. That's our formula. That's our slope. That's our intercept. Y prime is a predicted value. And the slope we call a regression coefficient. What do we call the difference between what the model predicts and what the actual y values are? Remember that term? Yeah? It's always you who answers this question. I asked it like 3 times. It's always you who answer this. I always remember. So, and what's the other word for the residuals? Epsilon, exactly. Okay, so our least squares method, again, is a vertical least squares. It's not orthogonal. So we're trying to find that line that makes all of these numbers combined as small as possible. So the error term, as mentioned, is a residual. And it's not a constant. It's a function, really. And it's defined by the difference between the predicted value and the actual value. And we have a standard error that is, in fact, the sum of the residuals divided by n minus 2 under the root sign. Using the standard error, we can now do a significance test for our slope. And the significance test really tells us if the slope is 0 or not. I argued it's not really that useful, but people tend to use it anyway. Because if it's 0, we tend to say that's not really a relationship. Anything bigger than 0 tends to be a relationship. But in my experience, 0 is a fine relationship. So I don't know what's going on. But the textbook does it, so we do it. Our t value is going to be our slope or regression coefficient divided by that standard error with the degrees of freedom defined by the total number of samples divided minus 2. We look it up in the back of the book and we compare it. As well, we can compute our Pearson's correlation coefficient. Remember, the R that we extract from a linear regression is a Pearson's correlation coefficient, not a Spearman's. It's not ranked. Using this formula here, we can get an R. Now, multiple regression. By the way, if I square my R, what do I get? I don't get variance, I get something else. Not variation, I get something else. Close. Something involving variation. Yes?
The other variable, like the amount of variation caused by the other variable.
Exactly. So the percentage of variation in the relationship that's explained by the other variable. So we want that as high as possible. That's the R squared. Anything above 0.6 is considered good. 60% is considered very good. Okay, so multiple regression is like linear regression, except it's a bunch of linear terms put together. And each of these is a regression coefficient. Obviously, we didn't compute multiple regression, but I want you to know where it is. We have an R as well in multiple regression. It's not a small r, it's a big R. And if I take my big R squared, what does that tell me? Same thing. It tells me exactly the same thing. It's the amount of variability or variation that soup of variables explains in this variable here. What's the difference numerically between the big R and a small r? Yes?
Big R can't be negative.
Exactly. Big R can't be negative. That's important. So the big R never tells us a directional effect. The reason for that really is we're talking about a multidimensional plane, and that has no actual physical meaning to us. So directionality has no meaning. So I just covered all that. Okay. Sample size calculation. Oh, and by the way, as I add more terms to my multiple regression, obviously my big R gets closer and closer to 1. Does it get closer to 1 faster or slower? Meaning, as I add a term, does the increment of change in my big R increase or decrease? Decreases, exactly. So as you add more, you gain more precision, but you gain more slowly. Right? So each addition costs you more, but there's a reduction in what you get out of it. Whew, all right. Sample size calculation we covered on Friday via the internet, and apparently the connection was poor. But the important part is that if you want to know how many subjects in your study, you compute power. How powered is my study? Is it underpowered? Is it overpowered? You can have all the subjects you want, but I can recruit 1 million subjects, but I haven't gained a whole lot after a certain point. There's a famous, did I tell you about the CMAJ study in Christmas time? CMAJ is the Canadian Medical Association Journal, used to publish in Christmas their jokey edition. It's real science, but it's jokey. And a few years ago, they published a paper that looked at, can you predict, or is there a relationship between whether or not you win the Nobel Prize in medicine and your astrological symbol? And they computed statistically that, yes, I think it was Geminis have a higher chance of winning the Nobel Prize in medicine. And all the Geminis will go, yeah, I'm going to win the Nobel Prize. But the actual interpretation is that with a large enough sample size, you can prove pretty much anything. So you're artificially increasing the chances of finding something significant. So there is actually a penalty for getting too many points on in your sample, but don't think about that too much. That's a little more complicated. Right. And we're doing survey samples. Really, you need about 1,000. 1,000 is the go-to number for surveys. So in the next political election, pay attention when the pollsters are repeating their data and talking about how we predict that this party is going to win so many votes. That's based on the ridings in a given province, and they're assuming this person's going to win that riding, that person, and it's based on opinion polls. However, to get an accurate sample from any riding, you need at least 1,000 respondents. It's impossible for anyone to pay for 1,000 respondents in every riding in the country. It is financially untenable. That is why our opinion polls are so poor at predicting winners. So beware when the pollsters come down and say, that guy's going to win. Ask yourself what the sample size was based on for their study. What they usually do is they use previous year's data, or they use a different kind of model to sort of beef up the numbers that they have, and it's very, very imprecise. That's why political polling is such a lucrative field to go into if that interests you at all, because the statistics are so weak, you need some additional insights to make them stronger. But there it is. Okay, so I gave you two important formulas. The first one is this: the number of people you need in a one-group study. That is, let's say you're going to determine if your group has a change in behavior relative to an external number. The example I gave was, will this drug change your blood pressure by X percent or X points? So it's one group only that we're testing. Then that's the formula. You need to know the variance, and we need to know the change that we're looking for. The change is delta. We square that. The variance is the standard deviation squared. Where do I get the variance, by the way? If I'm doing a study, I haven't collected any data yet. I'm doing this calculation to collect data. How do I know the variance of my sample if I haven't collected any data? Think about it. No ideas? You want to say something?
Then you look at a chart.
Look at a jar?
A chart.
What kind of chart?
Yeah. You always look at a chart in class.
Okay, where does this chart come from? The back of the textbook. No. Variance is the display of your data, the width of your data, the distribution of your data. You haven't got any data yet, but I need you to compute an n based upon a width of data that doesn't exist yet. So we're going to get it. Yeah?
Something to do with like the normal distribution?
Something to do with, that's always a safe answer. No. Yes. I'm sorry? Previous data, exactly. So, literature. This is why you do literature reviews, one of the reasons before you do a study. These guys here report that the variability in their sample was this, this, this. If it's a brand new sample, if it's a brand new subject no one's ever done before, or dealing with, beings, aliens from another planet that we never studied before, we don't know the variability is going to be, which is almost impossible to have a brand new study, by the way. Then what we do then is we do a pilot study. We get like 20 cases and do a quick little thing, variability is here. Because we need to have that seed data from somewhere to give us variance. Comes from literature. That's the easy answer. Something to do with the normal distribution. Right. So that's the formula for one group. If you've got two groups, however, like in a randomized controlled trial, and by the way, go back for a second. This is a very simplified formula. In real life, it's crazy complicated. And this formula only applies if we're looking for 80% power. That is, beta is what? What's the beta value going to be? For 80% power, beta is... What is beta? Type 2 error, exactly. So, remember what the relationship between beta and power is? Good thing we're having a review session. Power is 1 minus beta. Okay, so your beta here is obviously 0.2 then. So if we are setting our parameter at 80% power, it means our beta is 0.2. And we're setting our alpha level at 0.05, then this formula works. It does not work if those two situations are not in place. Okay, so if I give you a question, I will state that that's the case. If I've stated otherwise, then, be wary of it. Okay, so in that scenario, then, in a one-group situation, I can compute an n. Let's say I compute an n of 11.1. How many people do I need? 12, exactly. 11 is not enough because I need 11.1, and there's no such thing as 0.1 people, so it must be 12. Now, if I've got 2 people, it changes. The n per group is 16 times all that, not 8. That's per group. Right? So if I compute 11.1, if my n per group is 11.1, how many people must I recruit? 23? Because you've doubled 11.1 and you got 22.2 and you round up to 20. Well, no. Because per group is 11.1, there's no such thing as 11.1 people. So it's 12 per group, so it's 24. Right? Round first, then double. Yes?
Where do you get the delta from?
The delta, well, that's the difference we're looking for. So in this case, if I'm looking for enough people to detect, let's say it's a change in blood pressure of 10, then delta is 10. Delta squared is 100. I could always rephrase the question, because I'm an asshole, I will, and I'll say, I've got X numbers of people, and my variance was this. What difference can I detect? That's just a bit of algebra, shifting it around, okay? So be prepared to do some algebra. Otherwise, I'm just giving you numbers to plug into a formula, so some kind of thinking has to be involved here. In other words, it's a variable, it's an equation with 1, 2, 3 unknowns, and I can give you any number, any two of those 3 unknowns. You got to fill in the third one. All right? Yes.
What's delta?
She just asked that. Delta is the difference that we're looking for. So in the first example here, if it's one group, I'm saying I'm looking to see if my blood pressure changes by 10. Then delta is 10. In this group, I'm saying I'm looking for enough people such that the difference between the two groups is 10. Then delta is 10. Or it's 4, whatever it might be. Watch the units. Units matter. So make sure they're consistent. And I don't think I'm that big of an asshole that I would mess with the units, but I might have. I don't remember. I don't think so, but I might have. But people always screw up the squared parts. And the biggest trick of this is the rounding and remembering the difference in the two formulas, 8 versus 16. Okay, so which test to use here? Compare the mean IQ of men versus women among nursing students versus HSS students. This is, of all the tests that we have done since the midterm. So imagine now you're doing your independent fourth-year project, and you're going to do this. You've got to figure out what stats to apply. What stats are you going to apply?
2A and over.
2 and over. Why that? Why?
Because there's 2 variables.
It's two categorical variables. So there is a type of student, men and the gender, and you have a mean of a continuous variable. That is correct. 2A and over. Next one. The mean blood pressure between 5 ethnicities. What's that going to be? And why? Yes?
I know this
Why is that?
because you have one category, but more than.
That's right. It's one categorical variable. And that categorical variable is ethnicity. Don't be misled by the levels of ethnicity. There's only one variable here. Next one. Predict the final weight loss. There it is. It's an example I've given several times already. Right? So who's going to lose the most weight and the biggest loser? That's going to be multiple regression. Do this several times in class already. Well, oh, sorry, simple regression. Okay. So, is there a relationship between which faculty in which students are enrolled and which means of transportation they use? Ooh. So how do we go about looking at this one? First of all, let's look at the variables. What are the variables we're looking at here? Identify the variables. Which one are they? Bicycle is not a variable. That's a level. Yes?
Faculty and transportation.
Exactly. And what kind of variables are they? Categorical. So if we're looking for a relationship between two categorical variables, the test is a chi-squared. Exactly. Well done. That's how you do this. Predict the sex ratio of the nation of Bangladesh in 2050 based upon the values of a total base population in each year of the past decade. That's a tough one. Anytime we're dealing with prediction, that's a bad question, actually. That's an unfair question. I wouldn't phrase it this way. It's a bit misleading. Prediction, we're usually dealing with regressions. So it's some kind of regression. So in this case, it's a multiple regression. We have data from each of the past year. So we have, technically this should be what's called a logistic regression. So if this one confuses you, don't be too worried. It's a bit unfair. Okay, but what we have here is, on this side of the equation, the population distribution in 2050, and we have several linear terms. The first one is the population in 2049, here 2048, 2047, 2046. And each one of these is a continuous variable, and each one of these has an independent linear relationship with the 2050 data. And that becomes multiple regression. People actually have done this to predict the population growth in various countries. That's how it's done. And we throw in not just populations from past years, but other factors like their economic growth, maybe their sex ratio each year as well. Okay. Is there a relationship between the number of hours students spend watching TV and their relative standing in stats class? Ooh, well, that's curious. So relative standing, remember that one? That's like a Z-score thing, but we're not doing Z-scores because that's first semester. So in this case, relative standing is what kind of variable is that? It's an ordinal variable, right? And the number of hours students spend watching TV, it's continuous. So that's going to be a ranked correlation of some kind. So, because the second one is ranked. Now, you only know how to do Spearman's, so you'll do Spearman's, but technically that would be a tau. Okay, final exam is December 15th at 9:30 a.m. Now the big reveal is you get a cheat sheet, because that's so nice I am. We'll talk about the cheat sheet in a second. So, it's not going to help you. People, I got to cheat, I don't have to study. No, you got to study, trust me. Okay, here's your cheat sheet. You can bring one 8.5 by 11 sheet with anything you want on it, anything at all. Handwritten, printed, I don't care. Note from your mother, I don't care, right? Examples that we worked on in tiny microscopic writing, that's fine. If you can transfer the entire textbook onto tiny, tiny writing, go for it. In my experience, the act of making the cheat sheet is sufficient studying that you don't need the cheat sheet on the day of the event. That's why I don't care about a cheat sheet, right? So also, it prevents me from caring if you're cheating or not, because you're cheating already, you got the cheat sheet. You will not need stats tables, because I will give you the relevant tables, the F tables and stuff like that, T tables from the back of the book. Bring a textbook, bring a calculator rather. Again, not textbook. In the past, people actually have brought cartoons on a cheat sheet and things like that. So I don't care what kind of calculator you bring, so long as it's not communicating with people. Make it as programmable as you want. So, okay. On the final exam, the calculations you'll be doing, only the tests we learned since the midterm. These ones here. They'll be very similar to the ones you saw in your analysis assignment that's due today. The theory stuff, again, the stuff that we learned since the midterm, plus anything about type 1 and type 2 error, plus how to phrase null hypotheses, and plus how to use p-values. That stuff you will always need, so that transcends both semesters. Right? So the theory questions are very similar to what you saw in the midterm, and you all did well on that, so don't be too upset. The format, it's all multiple choice. I've forgotten how many questions. I think it's 100 and something. I don't know. It's a lot. People did find it difficult last year. Be different questions this year because the numbers are challenging. So just practice the numbers. Half computational, half theory. What to bring? Bring your cheat sheet. Again, both sides if you want. I always get questions like, can we print? Yeah, do whatever you want. Both sides, yeah, do whatever you want. I don't care. It's not going to help you. So, yeah, it's ominous, isn't it? It's not going to help you. Just don't spend too much time microscoping your cheat sheet and don't bother actually studying. Bring a calculator. Equations will not be provided this time because you've got space on your cheat sheet for including any equation you want. Okay, right? That's all. Any questions about anything? Yes?
Do we have to determine what statistical test to do? Like
Yes, you may actually have a couple of questions where you will determine which statistical test to use. Sometimes I tell you which, sometimes I don't. Yes?
Do we have to worry about ties and rank correlation?
No. No ties and rank correlation. Yes?
Won't be any questions like on SPSS. What
No SPSS questions. I may give you an SPSS output, where you have to extract the information, but I won't, no programming questions or SPSS use questions. Any other questions? Feel confident? Good. So don't forget, today at 2:30, if you want to talk to Laura, she's going over examples in E015. And Friday, no class, but I will be at my office. That is all. We'll see you on exam day.